In this optimization problem, we have a circle whose radius is 4, and inscribed in that circle is a rectangle whose dimensions we don't know. So this must be 4, and this must be another 4, so the diagonal of this rectangle, or the diameter of the circle, must be 8. Now, some things we know. Since we're trying to find the largest area of the rectangle, we know that the rectangle's area will have to be equal to x times y. And since this is a right triangle, we know that there is a relationship between x and y by the Pythagorean theorem. X squared plus y squared should equal 8. Or y squared should equal 8 minus x squared, or that y equals the square root of 8 minus x squared, which is the same thing as 8 minus x squared to the 1/2. So we're trying to maximize the area, and now we can write it completely in terms of x. The derivative of this, by the product rule, I'll have the derivative of the first, which is 1 times 8 minus x squared to the 1/2 power, plus the first function times the derivative of the second. I'll need to use the chain rule here. So this will be, the derivative of the second is 1/2 times 8 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. And when I clean up my derivative, I end up with 8 minus x squared to the 1/2 minus x squared over 8 minus x squared to the 1/2. I need to know when this equals 0, and this will equal 0 whenever these are equal to one another. 8 minus x squared to the 1/2 equals x over 8 minus x squared to the 1/2. Since it's a proportion, this would be 8 minus x squared equals x, or when 0 equals x squared plus x minus 8, which does not look like a fun thing to factor, and that's because it isn't. But I can use the Pythagorean theorem to solve for x. X must equal negative 1 plus or minus the square root of 1 minus 4 times 1 times negative 8 all over 2, where x equals negative 1 plus or minus the square root of 33 over 2. And the only possible value for x is the positive version, because since x must be a length, it has to be positive. So that will be x. Y then is not a major hassle to solve for. Y would equal 8 minus our quantity of x squared, so negative 1 plus root 33 over 2 squared, and then that whole thing to the 1/2 power. So this equals 8, and squaring that thing, I'm going to have will be over 4 when I square it. And squaring the numerator, we'll have 1 minus 2 root 33 plus 33, and this works out to be just something kind of messy. What is this? 32 over 4 minus 34 over 4. What a gross problem. Plus 2 times root 33 over 4. Or altogether 2 root 33 over 4 minus 1/2. Just a gross problem. Those would be the values for x and y. That would be the dimensions of the largest area rectangle. Now, second part of the question is, how would this change if the radius were r? Well, if the radius were just r, then that means that x squared plus y squared would equal r squared. Or y equals the square root of r squared minus x squared. And so we would have to do some different kinds of things to address this problem. We might have to consider what's going on with this circle. Well, we would know that the circle would have, everything would be in terms of r, and it would depend on the radius. Let's consider example 7, our final example for optimization. In our final example, we have a can of food, of cat food, that holds 6 ounces of food, and it has a volume of 14.5 cubic inches. How should this can be constructed so that the material made to make the can is a minimum? Right, so we want to hold a certain amount of food, but we want to make the can to use the smallest amount of material. Now notice that our cylinder has a radius, we'll call it r, and a height, we'll call it h. So a couple of things we know. The surface area of the cylinder is 2 pi r h, that tells us the label, plus 2 pi r squared, the area of both circles at the top and bottom. And we know the volume of of this is pi r squared h. And so what we have is we have 2 equations and 3 variables. Now we do know what the volume of the can is. We know the volume of the can is about 14.5 inches. And so we can choose to solve this for either h or for r squared. I'm going to solve this for h. And this means that h, the height, is equal to 14.5 over pi r squared. Which means our surface area, when we substitute that in, will be 2 pi r times 14.5 pi r squared plus 2 pi r. And simplifying, we will get 29 over r plus 2 pi r. So we have the surface area in terms of the radius. Well, the surface area, clean this up just a bit, will be 29r to the negative 1 plus 2 pi r. And we'd like to minimize this. I'm going to take the derivative with respect to r, negative 29 r to the negative 2 plus 2 pi. If I want to minimize this, I need to know when this equals 0. And this will occur when 2 pi equals 29 over r squared, or 2 pi r squared will equal 29, or r squared will equal 29 over 2 pi, or more importantly, the radius will be the square root of 29 over 2 pi, and that will be inches. Now that I know the radius, I can go back and figure out what the height of the can must be to hold the desired volume. So the height is 14.5 divided by pi r squared. We just figured out what we want the radius to be, the square root of 29 over 2 pi, and that whole thing will be squared, so the height will be 14.5 over pi times 14.5 over pi. Well, this ends up, pi's cancel out, and 14.5 over 14.5 is 1, so the height will be 1 inch. So we want to have a can whose radius is the square root of 29 over 2 pi inches, and whose height is exactly 1 inch. This will minimize the surface area, minimize the cost of actually making the can. There's our optimization problems.